Yeah, thank you for the introduction, and thank you very much for the possibility to speak at the Matroid Union. So I must say that I'm quite excited to explain my joint work with Matt Baker to you, to experts in Matroid theory. So Matt and I have background in algebra and number theory, so we came to Matroid series just a few years ago, and our understanding is still quite limited. We're working on that, but I think we can profit a lot from comments from your side, from feedback, and so to stimulate kind of discussions, I will also end the talk of today with some open problems and ideas for future developments. So in this sense, I want to encourage you to ask questions in the middle of the talk. At the end, you can also write things in the chat, as I said before, I have a second monitor, so you can follow the chat. Let's see if I have the intention to do so, but I hope every couple of minutes I can have a look if some question pops up in the chat. So maybe a fun thing first, something that you will notice is that Matt and I have a liking for wordplays. So the title of our talks contains two already. So we're not talking, as you have noticed last week, about the foundations of Matroid theory. I mean, there are several excellent accounts, and we're by no means qualified to do something like this, but we're talking about a mathematical object that's called the foundation of Matroid. And the name is derived in a very precise sense, and I will remark on that when we arrive at that point. And the other thing is that part 2 refers that this is the second part of our series of 2 talks. And it's not about the foundation of Matroids part 2, but still about the same paper that Matt and I put on the archive about a month ago. So being a sequel of Matt's talk, I will assume that you have been at Matt's talk in terms of motivation. So I will not give extra motivation for this talk, but I will just start right away. But I will not assume that you remember all technicalities, so I will remind you of the relevant definition throughout this talk. So I will take a different perspective. While Matt was taking part of the motivation aspect and try to gain your intuition for pastures and this object that we're dealing with from backgrounds that you might have in fields, partial fields, hyperfields, I will encounter the same objects from within the logic of pastures. So in a sense, I will provide you with cryptomorphic descriptions of the same objects. So they appear in a different shape in my talk. Well, you will see examples soon enough. Complicate my headphones. So let me start. The first part of the talk, first third maybe, will be quite algebraic. So I will provide background on pastures and will explain certain constructions that we need to do what we want to do in this talk. So as first thing, I will call the definition of pasture. And see, I forgot to put the highlighted cursor on. So just give me a second. So now this should be colorful. Yeah. So a pasture, to remind you, is an abelian monoid P multiplicatively written with an absorbing element 0. So this is an element that multiplies every other element of the pasture to 0. Together with the subset NP of triples in the pasture, modulo the permutation action of S3 that permutes coordinates. And this subset is called the null set. And rate A plus B plus C for an S3 orbit for a class of a triple, A, B, C. So you should really think of this as sum of 3 elements, and the sum is commutative, which corresponds to the S3 action, which satisfies the following 3 axioms. First of all, every non-zero element is a unit, is multiplicatively invertible. So this is something that has Pasture in common with fields. And you will notice that, I mean, the literal meaning of Pasture is some kind of field. And you should think of that also in the mathematical sense. The second axiom is that the diagonal action of P on this null set on triples or equivalence class of triples stabilizes the null set. And third axiom is that for every element A in the Pasture, there exists a unique additive inverse B, which means that A plus B plus 0 is in the null set. So you should think of all expressions in the null set as sums that are 0, that are null. Null is a German word for 0. Okay, here are a couple of conventions that I think Matt used for a large part in his talk as well. So normally we refer to Pasture just by the underlying monoid P, and we consider the null set as kind of a secondary object to which we refer by n sub P. And we write minus A for the unique additive inverse B, which appears in the expression A plus B plus 0 in NP. And we write something like A minus B for A plus minus B as usual. But all this has to be considered as formal expressions. And similarly, A plus B equals C means that A plus B minus C is in the null set. And the same goes for A plus B minus C equal to 0. So this is draws on our intuition for fields or partial fields, or if we substitute the equality by an element in relation, it encodes what's happening with hyperfields, but formally it just means that we get an element in the null set. So to conclude, the list of definitions. First an example, which is the only explicit example and the central example for today. The regular partial field, it's a monoid 0 plus minus 1 with obvious multiplication, together with a null set that consists of the two elements 1 minus 1 plus 0 and 0 plus 0 plus 0. Well, can verify the axioms right away if you still remember them. But this is the initial object in the category of pastures. So there's a unique morphism from n1 plus minus to every other pasture. So I should recall you what's a morphism. So this is just a structure preserving map. Or more explicitly, it's a multiplicative map from one pasture P to a pasture P prime that fixes the constants 0 and 1. And that maps the null set of P to the null set of P prime, where f of np is the map that's induced on triples. So for every a plus b plus c in the null set, the image is f of a plus f of b plus f of c. Okay, so far as the definitions of pastures, and I want to explain you now a few constructions on pastures that we need. The first construction is construction of quotients. So whenever we have a pasture P and we have a subset of triples in P modulo permutation of coefficients such that this subset doesn't contain any relation of the form A plus 0 plus 0, where A is a non-zero element. I mean, this would force a non-zero element to be 0, which we don't want. If we have given such a subset, then we can define the quotient as follows. First of all, we define an equivalence relation R on P that's generated by expressions of the form AC is equivalent to BC whenever A minus B plus 0 is an S and C is an element of P. So we have to multiply by C so that the quotient of P by this equivalence relation becomes a monoid again. So we denote by P double slash S, which is a quotient of P by S, S is quotient monoid, P modulo the equivalence relation, together with a null set that consists of all elements of the form class of A times D plus class of B times D plus class of C times D. Class means class in this quotient, P modulo R, where A plus B plus C is either in the null set of P or in S, and D is any element of D of P. And this forms a pasture, and it's a quotient because it satisfies the universal property of a quotient. So more precisely, it satisfies that whenever we have morphism F from P to another pasture P prime that maps the set S of new relations to the null set of P prime, then this morphism descends to a unique morphism from P double slash S to P prime, such that the diagram here on the right hand side commutes. So F is equal to mapping from P to the quotient by mapping an element A to the class of A, and afterwards applying F bar. So these are quotients, and we can already consider some interesting examples, starting with F1 plus minus. So we look at the quotients of F1 plus minus. So I wrote down a couple of examples. The first one is a field with two elements, F2. So it's clear in F2 we have 1 plus 1 is 0. So, but this equation is already enough to define F2 as a quotient of F1 plus minus. I leave this as an exercise. As I said, this is a kind of cryptomorphism of describing the same object in different terms. Matt had a different way to describe F2 in terms of embedding fields into the category of pastures. But it's really just a quotient of F1 plus minus by this single harmless relation 1 plus 1. I mean, note that this relation implies that 1 is the additive inverse of 1. So in the quotient 1 and plus and minus 1 become identified. So the monoid is just 0 and 1. And then you easily derive all additive relation of F2 from this single relation and the defining relation 1 minus 1 plus 0 of F1 plus minus. Okay, similarly, we can describe F3 as a quotient of F1 plus minus, which is this quotient by the single relation 1 plus 1 plus 1. It's clear 1 plus 1 plus 1 is 0, but once again, it's an easy exercise to verify that this encodes the whole binary operation of addition of F3. Then there's another pasture that appeared in Matt's talk, which is a Krasner hyperfield, which is also a quotient of F1 plus minus, namely by both relations that appeared before, by 1 plus 1 and by 1 plus 1 plus 1. So both relations hold. The underlying set is just 0 and 1, because this first relation forces minus 1 to be equal to 1. But we also have that 1 plus 1 equals 1, or that 1 plus 1 plus 1 equals 0. There's another example. I don't quite recall if Matt introduced it or not, which is a sine hyperfield. So this is the quotient of F1 plus minus by the relation 1 plus 1 minus 1. So in other words, 1 plus 1 equals 1 in the sine hyperfield, but we do not identify minus 1 with 1. Okay, there's some chats. Let me see. Okay, Matt already answered. So the question is if we can do this for all prime fields. In principle, yes, but they have more elements than just 0 and 1 and minus 1. So we have to introduce some additional variables. So kind of a primitive element for the field would be enough. So a generator of the multiplicative group, and then we have to divide out the relations for this generator. And normally, there's a surprisingly small number of relations that we have to inquire to get back the field. Okay, so let me pass to the next construction, which are free algebras. So this is as follows. given a pasture P and symbols x1 to xn, which we think of in determinants, then the free algebra over P in this n symbols, which are denoted by P angled brackets x1 to xn, is defined as a monoid which consists of 0 together with all monomials times some coefficient a in P star, so in a unit in P, where we allow the exponents e1 to en of the monomial to be integers. So these are, to be precise, Laurent monomials. We allow negative exponents. And the null set is just the null set, the minimal null set that's generated by the null set of P. So it consists of all expressions of the form ax plus bx plus cx, where a plus b plus c is in the null set of P, and x is any element of this monoid that I just described. So here we have to identify, if a monomial has a 0 coefficient, we identify it with a 0 element. So I'm a little bit suggestive in my definitions. I don't formalize things too much because this would just explode my notes, and I want to keep them nice compactly here. Well, this has the universal property of free algebras, of something like polynomial rings, or to be more precise, the analog of Laurent polynomials. Namely, whenever we have a given morphism from the pasture P to another pasture P prime, and elements A1 to AN in P prime that are invertible, so that are non-zero, then there's a unique lift of the morphism F to the free algebra P associate x1 to xn that maps the xi to the elements ai, and that extends the morphism F in the sense that if we take, I'm sorry, it's a little too much. If we map P to the free algebra by just mapping an element A to the constant polynomial A, then F is equal to this embedding followed by the lift F hat. Okay, this justifies to call this a free algebra. And now this free algebra construction paired with quotients allows us to write down more examples that we saw already last week. So to start with, there's an irregular partial field, which in the literature normally is denoted by U1, and we denote it by U because it plays a very central role in our theory, so we just allowed ourselves to drop the index to have as slim notation as possible. And as a quotient of free algebra, it's just f1 plus minus associate two invariant determinants, x and y, modulo the relation x plus y minus 1. So to see the connection to the usual definition as a partial field, note that this means that y is 1 minus x. If we use the convention of what I said before, that we can put one variable on the other side and change the sign of all other elements. And this means that 1 over x, not surprisingly, is x to the minus 1. This is tautology, but 1 over 1 minus x, which is the other element, appearing in the definition of U1 as a partial field, is y to the minus 1. Okay, so I leave the rest as an exercise for you to verify that these two objects are really the same. For this talk, you can just take it as a definition. The next example is the dyadic partial field. So within this logic that I just described to you, it's f1 plus minus associate one element z modulo the relation z plus z minus 1. So this means that z is an element 1 over 2, 1/2 in a sense, because if we embed this into a ring, then this is satisfied for 1/2, which kind of hints at the relationship, at the description as a partial field, which uses the dyadic integers to give this multiplicative subset. Now the next example. Somehow the scrolling is not smooth. Okay, the next example is a hexagonal partial field, or the standard name is the 6th root of unity partial field. But I think here comes Matt's and my liking for playing with words in and hexagonal. It's just smoother if you want, because you can form an adjective to it. So you can say this pasture is hexagonal or something like that. Besides the fact that the standard symbol S is already reserved for the sign hyperfield in our line of work, which plays an important role for oriented matrices. So we have a new letter H. So this is F1 plus minus associate Z modulo two relations. So it's Z plus Z to the minus 1, and Z cubed plus 1. So the latter relation means that Z cubed is equal to -1. And henceforth, Z to the 6 is equal to 1. And then you see very easily, I mean, in a field, these two relations are satisfied precisely by the primitive 6th roots of unity. I mean, 6th root of unity plus its inverse is equal to 1. So this adds a relationship to what's usually called the 6th roots of unity partial field. And it's really the same. And then as a concluding example, which is something a bit more complicated, but will also show up in our theory, that we consider is a two-regular partial field, which in our logic is a pasture which I denote by V. So we introduce again a different letter because of its importance for our theory, which is F1 plus minus associates 5 variables, x1 to x5, modulo 5 relations, which are the relations xi plus xi minus 1 times xi plus 1 minus 1, where I varies from 1 to 5. But the indices have to be read modulo 5, so x0 is x5 and x6 is x1 in this expression. And this is indeed isomorphic to the two-regular partial field if we embed this into the category of pastures. And this is really a non-obvious cryptomorphism or isomorphism. And in fact, we didn't realize this for a long time because, I mean, these descriptions are really so different until we notice that they satisfy the same universal properties, and therefore by categorical considerations they have to be isomorphic. Then if you sit down and see where to map these 5 elements, well, there are 30 fundamental elements in U2, which are not 0 and 1, so you just figure out a finite list of combinations, plus you do it a little smartly, and at some point you arrive there. Yeah, it's too much to write it down here, certainly. Okay, yeah, I think I continue here. At the end, you can ask me how to write F4 or F5 in this way. I don't want to lose too much momentum at the moment. So the next thing that I want to consider are subpastures. So subpasture of a pasture P, this is simply a submonoid P prime of P that satisfies that the absorbing element 0 is in P prime and that every non-zero element is a unit in P prime. So P prime minus 0 is a subgroup of P star. And the null set is just determined as a restriction of the null set of P. So it just consists of all elements A plus B plus C in the null set of P, such that A, B, C are elements of P prime. So that's a subpasture. And it's convenient that we just have to write down the monoid and the null set comes for free. As a last construction that appeared already in Matt's talk last week, I want to explain you what's the tensor product of two pastures. So given two pastures P1 and P2, the tensor product is defined as the following monoid. It's 0 together with the direct sum of the unit groups of P1 and P2 modulo the subgroup of order 2 that's generated by -1, -1. So it just contains -1, -1, and the neutral element 1, 1. And if we denote, we get a canonical inclusion from P1 and from P2 into the tensor product by mapping 0 to 0 and every unit to the corresponding element in the direct sum. So it goes into one column, into P1 star, P2 star. Then dividing out by the subgroup means nothing else than that we identify the images of -1 with respect to these two embeddings. And since -1 is something like a structure constant for a pasture, we should identify them to have a reasonable notion. This is something I forgot in the beginning. Matt introduced pastures with having an involution as an extra datum, but the involution is determined by the node set. A goes to -A by the involution. So I just skipped it from the picture, but this reappears here. So, we need a morphism that is invariant by the involution. So, -1 is really to go to -1, which requires its identification, because otherwise we have different candidates for -1. Okay, in the node set, it's basically the minimal node set such that these iota I become morphisms of pastures. So explicitly, the node set of P1 type tensor P2 consists of all expressions of the form iota IA times x plus iota IB times x plus iota IC times x, where I is 1 or 2, A plus B plus C is in the node set of PI, and x is any element of the monads that I just defined. When this tensor product is really a tensor product because it's a co-product in the category of pastures, like the tensor product of rings is a co-product of rings inside the categories of rings. So this means that for every pair of morphisms F1 from P1 to P prime and F2 from P2 to some other pasture P prime, there exists a unique morphism F1 tensor F2 from P1 tensor P2 to P prime, such that this diagram here on the right-hand side convenes. So we have the inclusions that I had before, and then this more F1 equals first inclusion, and then F1 tensor F2, and F2 equals second inclusion, composed with F1 tensor F2. Okay, so this was the first part on pastures, and now we are equipped with all the knowledge that we need to apply to matrix theory. So now I want to explain you what's the foundation of a matrix. So we fix a matrix M of rank R on a ground set E, a finite ground set, and I will denote the set of bases by split E sub M. So this notation is fixed for the rest of the talk, and I might not recall it at every point. So consider it as fixed. P is the pasture. And then first I recall a definition from Matt's talk last week, namely that of a P representation. So a P representation of M is a non-zero function delta from R tuples in E to the pasture P that satisfies the following three axioms. First of all, the support of delta consists precisely of those R tuples I whose underlying set is a basis. So the absolute value I is the underlying set, so the underlying set of tuple I1 to IR is just a set of coefficients I1 to IR. Particularly it's 0 if we repeat the same coefficient several times because the cardinality grows. The second axiom says that the function is alternating in the sense that if we have a permutation SR which acts on I by permutation of indices, then delta of sigma applied to I is equal to the sine of sigma times delta of I. Well, the sine of sigma is plus minus 1, and we consider plus minus 1 as elements of P to make sense of this equation. And then the third condition is that the three-term Plücker relations are satisfied. So for all R minus 2 tuples J in E, and for all elements E1 to E4 in E, we have this equation, that this equation here is in the null set. So these are the three-term Plücker relations, which also show up in the definition of Riemannian. Well, you might have seen it before or not, but this, as Matt explained, really encodes matrix representation. So a matrix M is representable over a partial field or a field, even only if there's a matrix representation. And it's orientable even only if there's a representation of a sign hyperfield in the set. So yeah, it just reflects the usual notion of matrix representations, therefore is meaningful. Okay, to this already lets us derive at the definition of the foundation. So first I define an auxiliary object, which is the extended universal pasture of M, which I denote by Pm plus. So this is F1 plus minus associate variables Ti, where I take symbol Ti for every R tuple in E, such that the support of the R tuple is the basis of M. So I varies through all elements in the support of such a representation delta, if you want. Modulo the relations T sigma I is equal to sine sigma times Ti. So this encodes the fact that representations are alternating functions. And the three-term Plücker relations. I don't write them out again, but it's really the same relation, but instead of evaluating delta in such a tuple, we write T sub J E I E J. So in the sense it's really the same relations. And then we, inside the extended universal pasture, we first find the universal pasture, which is the subpasture Pm that consists of all expressions of the form A times product Ti to the alpha I, where A is a constant in F1 plus minus, so it could be 0, 1, minus 1, with the condition that all the exponents sum up to 0. So it's a degree 0 part of this homogeneous pasture, if you want to draw from intuition of projective geometry. Okay, inside the universal pasture we find again another subpasture, which is now the foundation where we are aiming at, which I write by Fm, which consists of all elements A times product of Ti's to the alpha i's, which have multi-degree 0, which means that the coefficient can be any element, 0 plus minus 1. But now we want that all the coefficients sum up to 0 where I contains E for any given element, E in the ground set. So that's why multi-degree. For every element E in the ground set, we get a degree. And each of these degrees has to be 0. And from the definition, it's not hard to derive the following theorem. First of all, here's a remark. Why is it called a foundation? So, I mean, it's a wordplay, obviously, but it's derived from the fact that the foundation is a subpasture of Pm plus or of Pm that's generated by the fundamental elements in the sense of sample and liquid, which are elements A such that A plus B equals 1 for some other element B. So this was a notion that was developed for partial fields, and which has really a fundamental character to study matrix and representations over partial fields. And this led to the name of foundation, which also is, in a sense, a very foundational object for the theory, at least the line of thoughts that Matt and I are following in our work. Okay, quite easily derived from the definition is the following theorem. So first of all, the extended universal pasture represents P representations of M. So represents means it represents a functor that takes a matrix M, pasture P to the P representations of M. Which means there is a canonical bijection between these two. And this just follows immediately from the universal property of the free algebra combined with the universal property of quotients. Yeah, I don't go through the details, but this is really immediate. And from this statement can derive that the universal pasture Pm corresponds to the isomorphism class of P representations of M, and the foundation Fm corresponds to P rescaling classes of M. So I allow myself to don't recall these two notions that Matt explained in his talk. But this has the following important consequence, which is kind of the main argument for many applications. Namely, the matrix M is representable over P if and only if there's a homomorphism from Fm to P, a Pasture homomorphism. So the homomorphism set is non-empty. Sometimes we need to get really hold of how many homomorphisms are there when we want to do uniqueness arguments, but mostly we just care if the set is empty or not, if there's a homomorphism or not. One comment about the proof of 2 and 3. These proofs are not hard. They're basically derived from the fact that the degree 0 elements form a complete set of invariants for isomorphism classes. So this is just the passage from affine geometry to projective geometry, if you want. And the elements of multi-degree 0 form a complete set of invariants for rescaling classes. So this is something that comes up, for example, in the projective geometry of the plane, where the cross ratio is a unique invariant for rescaling classes. This comes back later in the talk in a certain shape. All I want to say here is that this is not a deep theorem. It's easy to prove. The deep facts come in a moment. So to approach the first deep theorem of the theory, I have to tell you what's embedded minor. Basically, you all know what it is, but we have to sharpen the terminology here a little bit. It's a minor together with choice of subsets that we exclude and contract. More precisely, if M and N are matrices, then an embedded minor of M of type N is a pair ij of subsets of the ground set of E that are disjoint and such that I is co-independent and J is independent. And the type N is isomorphism type of the minor M excluded I contracted J. So in this sense, it's an embedded minor. Formally, it's easiest to just say it's a pair of subsets of E, but we really refer with it to this minor here. And then if you switch the two words, embedded and minor, you arrive as a minor embedding. And we write this as if it was a morphism of matrix, but it's not comparable to a strict map of matrix or something. But it means it's an isomorphism of the matrix N with M excluded I contracted J for some fixed embedded minor I comma J of M. Okay, one first remark, which is probably obvious to the most of you. Every minor of N can be embedded. So every minor N of M is isomorphic to something of the form M excluded I contracted J, attention, where I is co-independent and J is independent. So normally we can take any disjoint subsets I and J, but then the Scum theorem allows us to shift elements between I and J so that without changing the isomorphism type of the minor, subset I becomes co-independent and J independent. Okay, so we're not losing somehow the picture of minors by taking this more specific definition. The importance for this definition is that we get a functorial behavior for foundations. In fact, for universal pastures, but I don't only care about foundations in this talk. So if M is a matrix of rank R on ground set E, then N is an embedded minor of rank S. So I write embedded minors now just as M excluded I contracted J, but assuming that it's really this pair of a co-independent I and independent J. And I fix an arbitrary ordering of the elements of J. So I write them as JS plus 1 to JR, but it's the number of elements equals the difference of the ranks, right? And then I can write down the association of elements in the extended universal pasture, T of J1 to Js, which is an element of Pn plus, goes to T J1 to Js, Js plus 1 until Jr, which is an element of Pn plus of the universal pasture. And this restricts to morphism between the foundations, these subpastures, Fn to Fm. And as a morphism of foundation, it's independent of the order of the J's, because the multi-degree assures that any possible sign change cancels out. If we reorder elements, the worst thing that we would arrive is at sign change, but in fact, it doesn't happen. So this tells us that embedded minors gives us morphisms of foundations. I would like to say embeddings, but in general, it's not an embedding. It could be that we have to quotient out things. But what's happening is the following. This is the first big theorem in the theory. If we have a matrix M on ground set E, then we define the collection script E as a collection of all embedded minus N, which are equal to M excluded I contracted J of M, on at most 7 elements with ground set En, which is E minus I minus J, such that when N has 7 elements, it's isomorphic to a Fano matrix or a dual Fano matrix. If N has 6 elements, then it's isomorphic to U24 plus U12. And if N has less or equal to 5 elements, then it contains at least a U24 minor, which implies that N has at least 4 elements, but I didn't write it down. So if we have this collection of very specific embedded minors, then we can write the foundation as the quotient of the tensor product of all the foundations of minors in this collection E, modulo relations, which are given very explicitly in the form that J of A is equal to A, or in other words, J of A minus A is a relation in S. So we are identifying this too. Whenever where J is a map between the foundation of N1 to N2, where N1 and N2 are in the collection E, so they're minors, embedded minors from M minus II contracted Ji, such that N1 is an embedded minor of N2. So I1 is in I2 and J1 is in J2, which allows us to write N1 as a minor of N2, which induces this morphism here. Okay, so just to repeat, we can write Fn in terms of the tensor product of all the small foundations, of the small embedded minors, modulo certain identifications which come from having kind of nested embedded minors. So we're just identifying elements whenever embedded minors are nested. Well, if you're a categorically minded person, then you will discover that this is simply the co-limit of the foundations of all embedded minors N in the family with respect to the minor embeddings between these embedded minors. Okay, but well, for calculations and for an explicit understanding is certainly better. Moreover, we can classify this Fn's for n in E as being either isomorphic to F2, the field with two elements, if n is a Farlow minor or a dual Farlow minor, being isomorphic to the two regular partial field if n is U25 or U35, and in all other cases it's U, the regular partial field. This gives us thought on calculating the foundation for any possible matrix in terms of small building bricks. And I should mention two names here which were really helping us to develop this theorem. So first of all, Rudi Pendery, who was aware of some form of this theorem, maybe not involving pastures, but who was aware of a statement like this and taught Matt and me how to prove it, basically. Yeah, I don't know if we would have arrived at that point or that quickly without really sad. The other person that I would like to mention here is Nathan Bowler, who was also very helpful with fishing out this date, improving previous statements, and also with other statements, but in particular with arriving at the theorem. So those were very helpful in this work. How to prove such a theorem? Well, the key steps are quite easily explained. First of all, one can see from one of the many equivalent definitions of the inner subgroup by Dress and Wenzel that it's isomorphic to the unit group of the foundation. So we can use the results about the inner subgroup to study the foundation. Then the first result, non-trivial result, is the observation by Dress and Wenzel that the inner subgroup is generated by the cross ratios, maybe together with -1, if it's not in the span of the cross ratios. So cross ratios are terms of the form Tj E1 E3, Tj E2 is 4, modulo the same terms where we switch 3 and 4. You can easily do the exercise and see that this element has multi-degree 0, and it generates the inner subgroup. The other theorem, which was published about 5 years later, or precisely 5 years later, is theorem by Gelfand, Rudnikov, Stone, which describes a complete set of multiplicative relations between the cross ratios. So this gives a description of the inner subgroups in terms of generators, cross ratios, and -1, and relations. And a remark that might comfort those of you who are dealing with presentations of matrices over partial fields and finite fields and rotor conjecture. Both theorems rely on Tutt's homotopy theorem. So the Tutt's homotopy theorem, which appears in this theorem we mentioned before, is built into the inner Tutt group, in a sense, or into the Pasture. So when Matt and I kind of derive certain statements very easily from our results, be reminded these results rely on Tutt's homotopy theorem and on these two theorems, which are all three of them quite complicated statements. I don't know if it's justified to say deep. I would say yes, but there's a lot of work going into that. So all what we have to do is to trace back the relations of Gelfand, Rudnikov, Stone to relations that appear in embedded minors. So this is not very complicated, this step. It's technical, so it's also not easy in a sense, but it's not deep. This is just a technical step. So one concluding remark regarding Theorem 8 is that there are similar descriptions of the Pasture in terms of the lattice of flats and the basis exchange graph, which is based on the fact that the foundation of simplification of a matrix is equal to the foundation of the matrix, and similarly for the dual of the matrix, and the direct sum of matrix, the foundation of a direct sum, and also of a two-sum is tensor product of foundations. mentions this already, but since the lattices doesn't, you know what I mean. So there are different cryptomorphic description of the foundation in a sense, in terms of flats of flats, basic exchange graph, and some other things that I didn't mention here explicitly. So let me now arrive at the structure theorem for foundations of matrix with large uniform minors, which is in some sense a central theorem of the paper that Matt and I published. And this is a theorem that Matt already cited last week. So if M is without large uniform minors, which means that there's no U25 and no U35 minors. And in consequence, it doesn't have larger uniform minors, of course. Then the foundation of M is isomorphic to a tensor product of Fi's, whereas Pasture's Fi are of one of the 5 types. It's either the near regular partial field U, the dyadic partial field D, the hexagonal partial field H, the finite field with 3 elements F3, or the finite field with 2 elements F2. But if M is uniform, then the foundation, if M is a regular matrix, then the foundation is F1 plus minus, and this is covered by the convention that the empty tensor product is F1 plus minus the regular partial field. But if M is not regular, then we will have positive number of factors here of this type. Okay, I go very briefly through the key steps of this proof, and then I probably have 2 or 3 minutes to mention some open problems to catch your interest. So first of all, since we don't have U25 and U35 minus, isomorphism type V doesn't appear for minus in our family E from theorem A. So these Fn's are either F2s or U's. And the other observation is that a Fano minor doesn't contain a U24. So whenever we have a morphism from N1 to N2 for 2 minors N1 and 2 in the family which are not equal, then this must be a morphism from U to U. And every morphism from U to U has to be an isomorphism, which you can check easily. So our system of embedded matrix, embedded minors and minor embeddings leads to a diagram of foundations of the following type. We have some isolated F2s, then we have some U's, which can be connected by isomorphisms. What can happen is that we have some kind of diagram which is cyclic. So this could induce a self-identification of U by some automorphism. So what we derive from this picture is that the foundation of M is isomorphic to, if you have disjoint components, we get a coproduct of Fn as a column. So we get a tensor product of some copies of F2 times tensor product of quotients of U by automorphism groups. So Hi is some subgroup of the automorphism group of U. Right. We can study these quotients. First of all, the automorphism group of U is a dihedral group D3 with 6 elements generated by a rotation rho of order 3 and a reflection sigma. And this has the following subgroups and the corresponding quotient. We have the triplet subgroup, so the quotient is just U tautologically. Then we have reflection subgroups of order 2, which are conjugates of subgroup generated by S. And in each case, the quotient is a dihedral partial field. Then we have the subgroup of all rotations, in which case the quotient is a hexagonal partial field. And we have the subgroup by all of these 3, in which case the quotient is F3, the finite field with 3 elements. So here we have all the factors of the theorem, and the theorem is proved. As a remark, all of these factors appear. So we know already the final matrix has foundation F2 from theorem A. Well, U appears as the foundation of U to 4. This is also implicit in theorem A. The dihedral partial field is the foundation of the non-final matrix. The hexagonal partial field is the foundation of the ternary FL plane. And F3 is the foundation of T8, where I use the notation of Oxford's book on matrix theory. And then using the direct sum of matrices lead to tensor products of foundation, we see that all possible tensor products of these factors appear as the foundation of some matrix. Okay, so this was basically the talks that I wanted to give and to explain what's the foundation and how to arrive at the theorem B that Matt used last week to deduce several statements about matrix theory. So in the last couple of minutes, I don't know when we started, it was a little bit late. Maybe I can talk for 5 more minutes, is that okay?
That's fine.
Okay, great. I want to talk about some problems. So maybe to take this away, of course, the first thing that comes to mind is now to consider a class of matrices that have U to 5 or U3 5 minus, maybe just one of them, or contain one of them as a stabilizer, or look at some particular class of matrices and study foundations and see what we can do with that. So this is certainly on our program to do eventually, or which, I mean, we are also happy to do in collaborations, or I mean, if someone is interested. So, I mean, we're really interested in interactions. So if you're keen of discussing things or interacting, please contact us. But there are some more particular theorems. One that Matt mentioned last time, which I want to pick up as the first one and maybe only one, is, let's start with the following fact. As M is quaternary and 3 connected, and Fn is a tensor product of 2 pastures F1, tensor F2, then one of the factors must be treated in the sense that it's isomorphic to the regular partial field or F2. And this follows from Kant's theorem about the unique representations of quaternary matrices together with theorem A. Well, I don't derive this here, but it's really easily derived here. So the question is, what happens more generally? If we skip this quaternary here? What happens for 3 connected matrices? So this would be an interesting problem. Matt and I had some ideas, but Nathan Bowler kind of destroyed all of them by showing that there's a 3 connected spike with foundation D tensor D. But still, there should be something true as the theorem shows, and I mean, 3 connectedness should be strong enough to say something about how the foundation can decompose into tensor product and how it can't decompose. That's important of all. So there are 3 possible approaches to tackle this problem. If we have a decomposition of the foundation of 3 connected matrices, so first of all, how we would like to imply it is to say that, well, there's a class of pastures P, which should be small, just all pastures, such that for all pastures P in this class, the homomorphism from one of this vector Fi to P, that there's at most one homomorphism, so that there's a uniqueness and all representations are governed by the other factor here. And well, I said it's the wrong way around. This class should be reasonably large and contain partial fields, the sign hyperfields, and some other things. But there are also pathological examples that we have to include, so it cannot be valid for all pastures. Then, if we look a little bit more under the hood, I mean, we would like to say maybe there's a class of foundations that now should be as small as possible, such that one of the factors must be in F. So this should be the class of trivial foundations. And we know from Nathan's examples and with other considerations that this class must contain all quotients of F1 plus minus and the dyadic partial field and the quotients. It's not clear to ask at all if we need to include other foundations in this list, if there is any non-trivial statement like this, so if we have some proper class of pastures that satisfies the statement. And then if we go deeper, we might look at the system EM of embedded minors to get some minor embeddings between these embedded minors. And then we could ask about embedded components of this system here, in the vein of the picture that I showed you before in the proof of theorem B. And then the to be 3 connected should have some implication on the connected components. So there are some trivial components, F2s, and maybe some dyadic partial fields, but the other should not be trivial. And this might be incorporated by enlarging the system, by including other little bit larger types of combiners, but still restricted in some sense, such that the graph becomes connected. I don't know. I mean, this would be finding a statement that we would like to reach, which is the closest to really the internal structure of the Pasture. Maybe I'm just selfish to spend 1 more minute on the second thing because it's just beautiful. We can split Rotha's conjecture into 2 subproblems. First of all, I don't read everything, no fear. First of all, we can look for excluded foundations for every finite field and hope that there's a finite list of excluded foundations. So excluded minors gives a list of excluded foundations by taking all the foundations. And then we can wonder a second problem if each of these excluded foundations has a number of minimal matrices with this foundation. And this is an exact splitting of Rotha's conjecture in 2 and might relate to some ideas of Jim Galen's talk from last month, where he said we have to organize somehow the excluded minors for F5 to have a reasonable picture because there are too many. So what I look to propose as an idea is to take the foundations as an invariant. So many of these excluded minors will have the same foundation, and this might result in a much smaller list that gives some more reasonable handle on that. Okay, I would stop here. Thank you for your attention.
Thank you. Are there any questions? Do you know if every finite field is the foundation of something?
I don't know, but I conjecture that this is true. I mean, we know that every finite field is a universal partial field of projective geometry, of the projective plane over the finite field. And if the foundation is a partial field, then it's isomorphic to the universal partial field. And I assume that this happens for the projective plane geometries, but I don't know. I haven't verified this. I didn't even think about that deeply.
Are there any other questions?
Yeah, I was just wondering if you've thought about joining 2 matroids with across a modular line. So if I have a modular line in one of the matroids and you attach it to another matroid by generalized parallel connection, can you say something about the foundations when you do this construction? So roughly why I'm asking this question is you have been talking about 3 connectivity, and I'm wondering whether this operation is sort of natural for foundations and maybe 4 connectivity is more natural than 3 connectivity.
I don't know. I mean, I don't know this construction. For parallel extension, you just get an isomorphism because you get, I mean, the first matrix is simplification of the other one. I mean, they have the same simplification, but I don't know this more general construction. So I don't know.
Yeah, I thought about this a little bit, but didn't completely work it out. But I think that it might be that, I mean, Oliver was talking about an absolute tensor product, but there's also relative tensor products. So you can have a tensor product over some other pasture. And I think that that might give a description of what happens when you join matroids along a suitable modular cut. And then, so sometimes that relative tensor product will happen to also be a tensor product. And there may be think about it in this way.
Are there any more questions?
I have a question. So this is probably a long shot, but okay, say you have two matroids on the same ground set and they have the properties such that every set that's independent in your first matroid is also independent in the second matroid. Does this have any kind of like interpretation in the foundations or anything like this? And the motivation for this comes from rigidity theory. I can expound on that if that's at all interesting. But yeah, is there any connection between like this ordering on matroids on the same ground set and their foundations?
I can just comment briefly on that, that when you relax a circuit hyperplane in a matroid, it's absolutely disastrous from a representation point of view. So it's not very promising because, I mean, that would be related in this way, and it'd be hard to believe that nice could be true.
Yeah, no, there cannot be a simple relation. I mean, you would like to define a morphism between this matrix with small, less independent sets to the other one by sending the variables there, but this doesn't work because the Plücker relations behave differently. But maybe there's a kind of common pasture that maps to both, and so you have a diagram of one map to the left and one map to the right, which connects these two things. So I'm not sure. I think something like this might be possible, but I don't know how helpful this would be. So, I mean, if you explain me maybe in later discussion more precisely what you want to do, then I can maybe give a more precise answer and think about it more profoundly.
Yeah. Yeah, if you want to do that offline or something, I can. Yeah.
Are there any more questions?
Just one comment. I mean, you've got this description of the foundations of matroids with no 5-point line or their dual as a minor. I wonder if there might actually be a real structural theorem about the matroids themselves. So, like whether we might be able to say precisely what are the matroids with no U25 or U35 minor. So ternary matroids would be one, and you get various things constructed from binary matroids by certain projections. But it would be nice if we had a precise structural description of the class. And I think your results sort of suggest maybe there should be.
Well, that would again be related to how closely the tensor product decomposition of foundations is reflected in the structure of the matroids, which is similar to what we're asking with this 3 connectivity problem. Should be something there, but there's work to do, for sure.
Well, if there are no more questions, thank you again, Oliver.